I am going to solve this integral using this substitution. The substitution that x is equal to negative cosine of 2t. So here, let's try to find an expression for the x in terms of t and dt. So this is negative. Differentiating is going to be negative 2 times the sine of 2t and then dt. So dx can be replaced with positive 2 sine of 2t dt. Alright, so this is what we have, and then let me switch colors and then we find the change in limits, right? So when x is equal to negative 1, that is the lower limit, we are going to have, you can plug it here, that is going to be negative 1 is equals to negative cosine of 2t. So that means that the cosine of 2t is equals to positive 1. So you can take the cosine inverse on both sides. So you have 2t is equals to the cosine inverse of 1. So 2t is equal to 0. That means that t is equals to 0 for the lower limit. So what about the upper limit? That is when x is equals to 0. We are going to have 0 to be equal to negative cosine of 2t. So that means that we have cosine of 2t to be equal to 0. So taking cosine inverse on both sides, we are going to have 2t to be equal to the cosine inverse of 0. And now 2t is equals to, cosine inverse of 0 is pi over 2. So that means that t is equals to pi over 4 for the upper limit. So now let's try to find an expression for the square root of 1 plus x in terms of t. This is equals to the square root of 1 plus x, and x is minus cosine of 2t. So that is going to be 1 minus the cosine of 2t. Alright, so from the double angle identities, we know that cosine of 2t is the same as the cosine square of t minus the sine square of t. So we have the square root of 1 plus x, and this is equals to the square root of 1 minus the cosine square of t plus the sine square of t. That is distributing in with the negative. And now from the Pythagorean identities, 1 minus the cosine square of t is the sine square of t. So sine square of t plus sine square of t, that is the square root of 2 sine square of t. So that means that square root of 1 plus x can be replaced with the square root of 2 times sine of t. Now, in similar fashion, let's try to find an expression for the square root of 1 minus x at the bottom. And that is equals to the square root of 1 minus x, but x is already negative cosine of 2t, so that is going to be positive now, cosine of 2t. So we have the square root of 1 minus x. This is equals to the square root of 1 plus cosine of 2t from the double angle identity, cosine square of t minus the sine square of t. And this is equal to the square root of 1 minus the sine square of t from the Pythagorean identities is the cosine square of t plus the cosine square of t. So that is just 2 times the cosine square of t. So this one is 2 times the cosine square of t. And the square root of 1 minus x, that can be replaced with the square root of 2 times the cosine of t. Alright, so the integral in the t world is now looking like this. So I is going to be the integral from the limits of integration is now from 0 to pi over 4. So the limits of integration from 0 to pi over 4 of the tan inverse of square root of 1 plus x. Square root of 1 plus x is the square root of 2 times the sine of t. This is divided by the square root of 1 minus x. The square root of 1 minus x is the square root of 2 times the cosine of t, multiplied by dx, and dx is 2 sine of 2t dt. 2 sine of 2t dt. So we see that 2 and square root of 2, those are constants. So 2 over square root of 2, when you are rationalizing the radical, is the square root of 2. The integral from 0 to pi over 4 of the tan inverse of square root of 2 times sine of t This is multiplied by sine of 2t from the double angle identity is the 2 sine of t cosine of t dt. And what is left at the bottom is the cosine of t. Cool. Now there's going to be a cancellation. Cosine of t is going to cancel out cosine of t beautifully. And now what you are left is this. I is equals to, this 2 is a constant, so that comes out, it becomes 2 square root of 2. The integral from 0 to pi over 4 of the tan inverse of square root of 2 times the sine of t. This is multiplied by sine of t dt. And now here I'm going to do integration by parts. I do the di, which is shortcut. So I'm going to differentiate this one because it's easier to differentiate that, which is the tan inverse of the square root of 2 times sine of t. And I'm going to integrate the sine of t dt. This is plus, next one is minus. Differentiating that is going to be, you have this. So what is going to be at the bottom is the square of this plus 1. So the square of that is 2 sine square of t, and now plus 1. And now I'm going to differentiate this one with respect to t and multiply at the top, which is the square root of 2 times the cosine of t. And integrating sine of t is easy. That is just the negative cosine of t. So what we normally do, we have to multiply diagonal terms. We are done with the integration, but when we multiply terms horizontally, we have to take the integral. Pi is equal to 2 square root of 2 outside. Now integration by parts, that is going to be multiplying terms diagonally. That is going to be negative tan inverse of the square root of 2 times the sine of t. This is multiplied by the cosine of t. Alright, we are done with the integration. Take the limits of integration from 0 to pi over 4. And now multiplying terms diagonally, we have to take horizontally, we have to take the integral, but it's positive because of these two negative signs. Alright, so we have the integral from 0 to pi over 4. Now let's multiply them. That is going to be the square root of 2 times the cosine square of t. This is divided by 2 times the sine square of t plus 1, and then dt. All this one is multiplied by 2 square root of 2 in front. I is equal to, now let's distribute in with the 2 square root of 2. We have negative 2 square root of 2. And now the tan inverse of the square root of 2 times the sine of t. This is multiplied by the cosine of t. The limits of integration from 0 to pi over 4. And now this square root of 2 will come out and multiply 2 square root of 2, and that is going to be 4. The integral from 0 to pi over 4 of cosine square of t. This is divided by 2 sine square of t plus 1 dt. So far so good. Now let's evaluate the limit. So in evaluating the limit, we have negative 2 square root of 2, that one out. And now let's plug in the limits. That is going to be the tan inverse of square root of 2 times sine of t. So sine of pi over 4, that is going to be the square root of 2 over 2. That is the sine of pi over 4. This is multiplied by cosine of t, and cosine of pi over 4 is going to be square root of 2 over 2 as well. This is the upper limit minus the lower limit. So the lower limit, when you plug in 0 here, that is going to be the sine of 0, which is 0, and tan inverse of 0 is 0. And 0 times cosine of 0 is 0. So this is 0 for the lower limit. Plus 4 times the integral from 0 to pi over 4. This is multiplied by the cosine square of t divided by 2 times the sine square of t plus 1. This is the integrand. Okay, so we have I to be equal to negative 2 square root of 2. And now we have this square root of 2 times square root of 2 is 2 divided by 2, which is 1. So we have tan inverse of 1. And tan inverse of 1 is pi over 4. So we are going to have pi over 4 multiplied by the square root of 2 over 2 as the limit, plus 4 times the integral from 0 to pi over 4. And this is the integrand, the cosine square of t all over 2 sine square of t plus 1 dt. Alright, cool. So this one will simplify to negative pi over 2. because this and this will multiply and will cancel this, and we have 2 cancelling this one, leaving 2. So what is left there essentially is just negative pi over 2. Alright, plus, I'm sorry, this is 2, negative pi over 2 plus 4 times the integral from 0 to pi over 4 of the cosine square of t divided by 2 sine square of t plus 1 dt. Alright, so now I'm going to call this one integral I1, and now I'll solve that. So permit me to call this one equation star because we'll have to come back to it later on. Okay, so equation star, and now we are going to solve I1, which is the integral from 0 to pi over 4 of the cosine square of t. This is divided by 2 sine square of t plus 1 dt. So now let's do a substitution here. Why not? So the substitution that I'm using for this integral is I am going to let let's say y to be equal to the tan of t, right? So this is what I'm using. So this is the same as y over 1, right? So that means that here t is going to be equal to the tan inverse of what? Y. So we can find an expression for dt, which is going to be 1 over 1 plus y squared dy. So I have an expression for this. Now let's find the change in limits. So the change in limits, when t is equal to 0, we are going to have y to be equal to the tan of 0. Tan of 0 is 0, and when t is equal to the upper limit, which is pi over 4, y is going to be equal to tan of pi over 4, which is 1. And now let's find an expression for the sine and cosine of t in terms of y. So this is the right triangle, right? And our angle here is t, and now tan of t is y over 1, and tan is opposite, which is here, and adjacent to the angle is here, and the hypotenuse using the Pythagorean theorem is going to be the square root of the sum of squares of the other two sides. So the square root of the opposite squared and the adjacent squared. And now we can find the sine and the cosine of t. So the cosine of t here is going to be adjacent over hypotenuse, which is 1 over the square root of 1 plus t squared, 1 plus y squared, I beg your pardon. And now the sine of t here is going to be y all over the square root of 1 plus y squared. This is cosine of t and the sine of t in terms of y. So the integral I1 is equal to, this is the integral from 0 to 1 now. This is now the integral in the y world of cosine square of t. So cosine of t is 1 over the square root of 1 plus y squared. This is squared divided by 2 sine square of t. Sine of t is y over the square root of y squared plus 1. This one is squared as well. And now plus 1 multiplied by dt. dt is 1 over 1 plus y squared dy. Now let's simplify this one because it looks a little messy. So the integral from 0 to 1 of this one is now 1 over 1 plus y squared. This is divided by, this is, the bottom is 2y squared all over 1 plus y squared, or y squared plus 1, like the same thing. And this is added to 1 multiplied by 1 over 1 plus y squared dy. Cool. So I1 is equal to the integral from 0 to 1 of 1 all over 1 plus y squared. This is divided by, so this one is now 2y squared plus y squared plus 1. This one is divided by 1 plus y squared multiplied by 1 over 1 plus y squared dy. Alright, so there's going to be a cancellation here. So this one is going to cancel this one out. And now what you are left is this. I1 is going to be the integral from 0 to 1 of, we now have 1 over 2y squared plus y squared is 3y squared plus 1. And this is multiplied by 1 plus y squared, like this. and then dy. Cool. So now this is what our integral has been reduced into. So now here we can apply partial fractions. So let me switch colors again and we look at the partial fractions. So the partial fractions, I'm just going to look at the integrand and then I'll come back later on for the integral. So the integrand is 1 over 3y squared plus 1. And this is multiplied by 1 plus y squared. So this is equal to partial fraction decomposition. This is going to be y plus b. This is divided by the first factor, 3y squared plus 1, plus the next one is going to be cy plus d divided by 1 plus y squared. Alright, so here 1 over 3y squared plus 1 multiplied by 1 plus y squared. This is the same as doing cross multiplication. We have ay plus b, and this is multiplied by 1 plus y squared, plus cy plus d. This is multiplied by 3y squared plus 1. All this one is divided by the LCM, which is the product of these two quadratic terms, 1 plus y squared. Alright, so 1 is equal to the denominators are the same, so we just have to FOIL those on top. So that is going to be ay plus ay to the third plus b plus by to the second plus this is 3cy to the third plus cy plus 3dy squared plus d. So now let's gather like terms. I is going to be equal to a plus 3c. This one is the coefficient of y to the third, that is this and this. Next is going to be the y squared term, that is going to be b plus 3d. This is y squared. What about the coefficient of y? That is going to be a plus c. This is y, and the constant term is b plus d. So now we can compare both sides. There is no coefficient of y to the third on the left, the same as y squared and the same as y. So those ones is going to be 0. So we have a plus 3c. This is equal to 0, equation 1. We have b plus 3d. This is equal to 0 as well, equation 2. We have a plus c. This is equal to 0, which is equation 3. And then the last one, b plus d, the constant is equal to 1. The constant term on the left is equal to 1. That is what we have. And now when we solve these four equations simultaneously, the values of a, b, c, and d that will satisfy them will be a is 0, b is equal to 3 over 2, c is equal to 0, and d is equal to negative 1 over 2. So this is negative 1 over 2. So you can verify by plugging in the values, and that will be the values for these a, b, c, and d that will satisfy the equations. So now let's go back to our partial fractions. So the partial fraction is here. So we have ay plus b over the first factor. So we have 1 over 3y squared plus 1. This is multiplied by 1 plus y squared. This is equals to now ay plus b divided by the first one. So ay plus b. So a is 0, y plus b, and b is 3 over 2. This is divided by the first factor, 3y squared plus 1. And now the next one is cy plus d divided by the second factor, cy plus d. So c here is 0, so 0 times y plus d. So that is going to be 1/2 divided by the second factor, 1 plus y squared. So 1 over 3y squared plus 1 multiplied by 1 plus y squared. This is the same as 3 over 2 multiplied by 1 over 3y squared plus 1. And now this is minus 1/2 times 1 over 1 plus y squared. Alright, so now we can integrate. So remember, we are now integrating from 0 to 1 of that. So this has now been reduced to this. So our integral I1 is going to be the integral from 0 to 1 of this. So that is going to be 3 over 2, 1 all over 3y squared plus 1 minus 1 over 2 times 1 over 1 plus y squared. All this one dy. Now let's split this one into two different integrals. I1 is going to be equal to 3 over 2, the integral from 0 to 1 of 1 all over here. I'm going to factorize 3 out, and that is going to be left with y squared plus 1 over 3, like this. This is the first one, and the second one is minus 1/2 in front, the integral from 0 to 1 of 1 over 1 plus y squared. This is just the arctan of y, the second one. But the first one is a little bit tricky. So 3 over 2, now permit me, this 3 here, I'm going to pull it out. I'm going to have 3 over 2 times 1 over 3. That is this 3 coming out here. So we have the integral from 0 to 1 of 1 all over y squared plus 1 over 3 can be written as 1 over the square root of 3, all this one squared, and then dy minus 1 over 2, the integral from 0 to 1 of 1 over 1 plus y squared dy. Now that we have this, everything is easy. And now the first one, we have the integral of 1 all over x squared plus a squared dx. This is the same as 1 over the constant and then multiplied by the arctan of x over the constant. So the first one is just like what we have here. So we can apply that same principle to solve this integral. This now has now been reduced to 1/2. So this is 1/2. But in now solving this integral, we have 1 over a. A here is 1 over the square root of 3. And now we have the arctan of y over the square root of 1 over the square root of 3. Like this. The limits of integration from 0 to 1 minus 1/2. This one is just the arctan of y. The limits of integration from 0 to 1. Let's plug in the limits. This one is going to be the square root of 3 over 2. That is the reciprocal of that. And now we are going to have the tan inverse. So here is going to be plugging in the limits. That is going to be the tan inverse. That is the upper limit first. The tan inverse of 1 over the square root of 3. And now minus, plugging in 0, tan inverse of 0 is 0. Minus 1/2 tan inverse of 1 minus tan inverse of 0 is 0. Alright, so I1 is going to be equal to the square root of 3 over 2, and this is multiplied by, this is now the tan inverse of the square root of 3. Minus 1/2 the tan inverse of 1. So let me write it again, and then we can now simplify everything in the next line. So I1 is going to be equal to the square root of 3 over 2. Tan inverse of the square root of 3 is pi over 3, because tan of pi over 3 is the square root of 3, and the tan inverse of the square root of 3 is pi over 3. Minus 1 over 2 times tan inverse of 1 is pi over 4. So this one is simplifying to square root of 3 pi over 6 minus pi over 8. Alright, so this is what we have for I1. So then let's switch to white pen and now wrap up the integral. We are going back to equation star. So equation star here is I is going to be equal to negative pi over 2, right, plus 4 times I1. So negative pi over 2 plus 4 times the integral I1. That is I, what we are looking for. That is equals to negative pi over 2 plus 4 times integral I1. So I is equal to negative pi over 2 plus 4 times I1, and I1 is the square root of 3 times pi all over 6 minus pi over 8. Now let's simplify this one. I is going to be negative pi over 2 plus, multiplying with 4, we are going to have 4 square root of 3 pi all over 6 minus, this is 4 pi over 8. 4 pi over 8 is the same as pi over 2. So this one is negative pi over 2 minus pi over 2. That is this one. And now we are going to have plus, that is going to be 2 square root of 3 pi all over 3 at the bottom. Negative pi over 2 minus pi over 2 is going to be negative pi. And now plus 2 square root of 3 pi over 3. And now what you have is the result for this integral, which is 2 square root of 3 over 3 minus 1. All this one multiplied by pi. And this one is the beautiful answer to this beautiful integral. Yeah, so that is how I solved this integral. If you find this helpful, consider subscribing to Calculus Diaries and give me a thumbs up so that I'll continue uploading engaging tutorials on calculus. I thank you so much for watching this video, and I will see you in the next one. Bye bye.